All right, hi guys, I'm Paul. I'll be presenting computational wiretap coding from indistinguishability obfuscation. This is joint work with Yuval Ishai, Ayush Jain, Amit-Sahai, and Mark Zandri. So before we talk about the general wiretap problem, I'm going to give you a special instance of it. And it's going to be inspired by coding theory. It's this question of, suppose I have a code word from a random linear code, so the C of x, and I'll send it through a binary symmetric channel with error rate 0.1, meaning that every position of C of x is going to be flipped with 0.1 probability. And we believe that decoding from this noisy code word is computationally hard. This is captured by the LPN problem with constant error probability. However, if we send this same code word through a binary erasure channel with erasure rate 0.3, where every position is erased with 30%, then if this code word is long enough, you can run Gaussian elimination by just guessing some error-free positions and recovering x. And in general, in classical coding theory, we know that recovering from erasures is easier than recovering from errors. However, we can ask a reverse question. Do there exist error-correcting codes that satisfy the following property? It's easy to decode from 0.1 bit flip error rate, but computationally hard to decode from 0.3 erasure rate. And just from this example of Gaussian elimination, we know that linear codes fail. So these examples where we already know that it's easy to code from 0.1 bit flip rate don't satisfy the second property. Okay. And until 2022, we didn't know of any such codes that satisfied both such properties. But in a prior work, we showed that in the ideal obfuscation model, or assuming non-standard VBB obfuscation assumptions, for example, about evasive functions or fuzzy point function obfuscation, then VBB for generalized fuzzy point function obfuscation, then we actually have such codes. And in this work, we showed that we actually can still say yes, just assuming well-studied hardness assumptions by going through I/O. And you might be asking, what is this asterisk? Well, in classical coding theory, the encoding function is deterministic, whereas our encoding function will be randomized. So let me tell you about the general setting of the wiretap channel. This was introduced by Weiner in 1975. And here we have Alice, Bob, and Eve. Alice wants to send a message to Bob, and Eve is listening in on a wiretap. So think of there's a copper wire running from Alice to Bob, and Eve has attached an alligator clip to this wire somewhere. And Alice will encode her message M, send it through this wire, and it will go to both Bob and Eve, to Bob through channel B, and to Eve through channel E. And somehow, Bob should be able to recover the message, but Eve should not. And as some clarifications, both channels are discrete memoryless channels. They don't remember any state. There's no interaction, so we don't assume Bob has a clear channel he uses to pass back any information. And there's no shared secrets. So Alice and Bob don't have any shared randomness. There's no public key infrastructure. There's no shared keys.
In the classical wiretap channel, both are with binary symmetric noise.
Yes.
One of them is more noisier.
Yes, so here we're going to study general channel pairs beyond just the BSC with P0 and BSC with P1.
But
Great.
is B and the E here at the end of channel, is it erasures or is it eavesdropping?
Good. B for Bob, E for Eve.
Oh.
No erasures. Oh, well, yeah,
No erasure.
not erasures. Yes.
Not binary symmetry.
Yes. Any other questions?
Eve sees 30% of the bits erased.
Yep.
And Bob sees 10% flip.
Exactly. Okay. So we're going to ask a feasibility question, which is, for what pairs of channels do wiretap coding schemes exist? And let's start with the intuitive impossibility result for the case of a BSC 0.1 for Bob's channel and a BC 0.2 for Eve's channel. So just observe that here in this setting, Eve has as much information as Bob, because she'll receive something with 0.2 fraction erased, and she can just flip bits. So she can simulate perfectly Bob's channel output. So intuitively, there's no advantage for Bob. And in general, this is true whenever Eve can perfectly simulate Bob's channel output. And we call these channel pairs degraded channel pairs. So in this setting, we say that channel B is a degradation of channel E, if and only if Eve can perfectly simulate Bob's channel with her channel. Yes?
So, sorry, and why is this the right model? Like intuitively, why is erasure for the adversary and flip for the honest party? Why is that the right model? What is that?
Right model in what sense? Like, this is just a toy.
An example of
Yeah.
this.
So we'll study the general setting. We're just going to give this as an intuitive, easy to understand example. And it will actually convert, you'll see, into kind of the central question for all binary input channel pairs. Any other questions? Great. OK, so one can naturally ask, we have this triviality, which is if you have a degraded channel pair, there's no wiretap coding scheme. Is it true that for every non-degraded channel pair, you can get wiretap coding schemes? And so let's first ask this information theoretically. So this was actually resolved, completely characterized in a work of Cesar and Corner in 1978. And they showed that, surprisingly, there are non-degraded channel pairs that do not have statistical wiretap coding schemes. So by statistical here, we mean that Eve is computationally unbounded. Yes. So an example of a non-degraded channel pair that does not have a information-theoretic wiretap coding scheme is exactly this case of BSC 0.1 and BEC 0.3. And the question, of course, is can cryptography enable wiretap coding schemes for a larger class of channel pairs? And in a previous work, we show that if you assume ideal obfuscation, then there exists a computational wiretap coding scheme for all non-degraded channel pairs. And notably, this includes our teaser case. And now the question is, can we obtain computational wiretap coding schemes from well-studied assumptions? And in this work, we show, yes, assuming the existence of indistinguishability obfuscation in injective PRGs, there exists a computational wiretap coding scheme for any pair of non-degraded binary input channel. So the input alphabet for both channels is 0, 1. Great. And this solves, again, with the asterisk, meaning that we have a randomized encoding rather than a deterministic coding, the teaser problem. OK. So just an overview of the techniques. We're going to use I/O and injective PRGs to construct a Hamming ball obfuscator. And this construction will use a new gadget, which we call PRG with self-correction. And then using this gadget, we're going to build computational wiretap. Oh, using this gadget, we'll build computational wiretap coding schemes for the binary asymmetric channel and the binary asymmetric erasure channel. And someone might ask, why is this a central case to all pairs of binary input channels? And to show this, we'll actually introduce a polytope characterization, but we're only going to use it in 2 dimensions, so hence polygon. We introduce a polygon characterization of degradation. And using this polygon characterization, we'll show how to reduce the problem of constructing a computational wiretap coding scheme for any non-degraded binary input channel pair to just the case of BAC, BAC. OK.
Is there some intuition for the information-theoretic impossibility, like 1.3? I mean, it's probably not related to your talk, but I'm just curious.
For 0.1.3, I would have to, yeah, I'm not sure. It's related to this, yeah, I'm not sure. I don't have any.
What is the smallest number for which you can do it? Or, I mean, is there something, for which you can do information theoretic?
So there's this secrecy parameter threshold that you can compute, but in general, it's very difficult to compute. But for the case of BSC, BEC, it's quite simple. It's pretty much whenever one is, for the,
If you change 0.3 by 0.36 or bigger,
yeah,
it's possible.
yeah. So basically, it's something like 4p, 1 minus p, whenever e is greater than 4p, 1 minus p.
This is tight?
This is tight, yeah. And this is partially due to Cesar-Corner, but the actual computed values for the 4p1 minus p are due to Chandran in 2010, I think.
But when you say tight, I mean, constructively, we don't have an efficient scheme, right?
No, no.
Exactly.
Yeah,
Yeah.
that's right.
For the lower bound, of course.
Yes. Great. Okay. So the focus of this talk will be presenting the construction for the symmetric case. And then I'll have one slide on how to convert that into the asymmetric case. It's quite simple. And then we'll talk about how to view this polytope characterization. Okay. So what's I/O? We've seen this a million times. But I/O just takes two circuits that are functionally equivalent of the same size. And if you I/O both of them, they're computationally indistinguishable. And we know them from well-studied hardness assumptions now, thanks to Jain-Lin-Sahai. And let me introduce this new gadget, which is called a PRG with self-correction. And it satisfies the standard properties of a PRG, polynomial stretch and pseudorandomness. And it also has this epsilon self-correction property, where if I give you the PRG evaluated at some seed seed, and I also give you a string seed prime that agrees with the seed on at least half plus epsilon fraction of bits, think of epsilon as a constant, then you can efficiently recover seed. And for this talk, think of epsilon being 1/12 for the case of BSC 0.1, BEC 0.3. And you might be asking, do we already know examples of SC PRGs or candidates? And Bogdanov and Chow showed in 2012 that the Goldreich PRG, even with linear stretch, is a self-correcting PRG, or a PRG with self-correction. And in our work, we'll show how to construct a injective SC PRG from any injective PRG. Okay. So let me recall the construction, the encoding scheme for a computational wiretap coding scheme using ideal obfuscation. And then we'll just see if we can replace ideal obfuscation with I/O. So in the previous paper, we showed that the encoding consists of two parts: a uniform random string R and some ideal obfuscation, VBB obfuscation of f sub R, which is this Hamming-Ball function that has two things hard-coded into it. It has the center point R hard-coded into it, and it has the payload M hard-coded into it. And you can think of Bob and Eve as having input-output query to this function. And the idea is that R, when it's sent through both channels, Bob will have approximately 10% of it flipped. Eve will have about 30% of it erased. And Bob can just plug his received string, R sub B, into this function. And by just a standard turn-off bound, you know that this inequality will be satisfied with overwhelming probability, so you can recover the message n. And Eve's best guess for R will be, this should be R, has about a 0.15 error rate, and that's much too high. So, and then if we're using ideal obfuscation, both the hard-coded values R and M are completely hidden. So that's security. And now the question is, can we just replace this with I/O? And the question really is, why would I/O of this Hamming-Ball function actually hide both the payload and the center point R? Yeah. Okay, so let's take a look at what Eve sees. So Eve sees some received string R sub E with erasures, and also receives this I/O'd function, Hamming-Ball function. And Eve, of course, doesn't know these red positions, 1, 0, 0. And if you wanted to just puncture point by point, you can't. There are just exponentially many points in this Hamming-Ball, so the standard puncturing technique fails. But the idea is we're going to use some sort of hybrid argument, again, to show that this circuit is no different from the null circuit. Intuitively, this is an evasive function. It's difficult for you to pinpoint something that would not output bot. And the critical observation is that in intermediate hybrids, we can actually have the circuit depend on the received string, R sub E. And I'll show you how we do that. So we're going to look at R sub E, split up the indices into erased positions and non-erased positions. And intuitively, you know that the only thing that matters to Eve is the erased positions. So we're just going to only focus on those positions. And so this is we're going to construct an indistinguishable viewpoint. And the first thing we're going to do is change the description of this function. So we're going to split the hard-coded R into just the substring defined by the indices S sub 0, 1 and S bot, and have this set of indices hard-coded into the function. So far, nothing's really changed. And we're also going to rewrite the Hamming distance, just additively split it. And by I/O, this function is indistinguishable from the previous because it's functionally equivalent. We've done nothing but rewrite the description of this function. And just observe that for this portion, Eve knows all the non-erased coordinates. So this thing, for all intents and purposes, will always be 0. And Eve's best strategy, because R was picked uniform randomly, is to guess randomly for R prime S bot, because zeros and ones are equally likely. And we'll revisit this when we get to the asymmetric setting. And again, observe just even for that portion, there are exponentially many guesses that cause the function to output M, so still no puncturing. And we're not going to use puncturing at all. And instead, what we're going to do is we're going to compress all of these into a single branch that can be removed by a hybrid argument. So what's the idea? We don't want this RS bot hard-coded in this function, because that's exactly what Eve shouldn't be able to see. So let's cut it out. We cut it out. And now the question is, how would you compute this conditional branch here? And the idea is, like, you obviously have to give some hint. So what we're going to do is we're going to put the SC-PRG on RS bot as your hint. And nicely, this has a self-correcting property that says if you gave some input R prime or S sub bot that's close to this original seed, you're actually able to recover the correct value of RS bot, and then therefore compute this conditional branch. So that's exactly what we're going to do. We're going to recover, run the recover function on this SC-PRG with the input corresponding to this S sub bot positions. And then we're going to use the injectivity of this SC-PRG to actually check that we have the correct value. If not, output bot. And otherwise, just compute the same functionality as before. So by the correctness of the SC-PRG recovery, this is functionally equivalent, and we use the I/O indistinguishability to argue that this viewpoint is indistinguishable. Good. And just observe now that from Eve's point of view, RS bot is an unknown uniform random string, because we've cut it out. And therefore, we can just apply the pseudo-randomness property, and this is indistinguishable with a PRG. And then, since it's length tripling, we know with overwhelming probability, R is not in the image of SC-PRG with overwhelming probability, so this will be functionally equivalent to the null circuit. And that's it. Okay, so let's talk about the SC-PRG. Yeah.
I think I probably missed that. Why were you saying you cannot do puncturing one point by another? I missed that point.
Yeah, so there are exponentially many points. So you would have to, maybe there's like some sort of parameter choice, but I don't see a way of.
Oh, you mean it would influence the size of the encoding?
Yeah.
I see. Okay.
Yeah.
Got it.
Okay. Good. So let's talk about the code offset construction of the SC-PRG. You'll see these code offset constructions from like the works of Benjamin Fuller on fuzzy point obfuscation, stuff like that. But you start with an injective PRGG and a list decodable error correcting code C for up to half minus epsilon error rate for any constant epsilon greater than 0. And we know an example of this by just concatenating a binary Reed-Solomon code with a Hadamard code. And this SC-PRG, think of a long part of the seed, S1, and then a shorter part of the seed, S2. And what you're going to do is you're going to output S1 plus C of S2, and then G of S2. And pseudo-randomness is pretty straightforward. Since S1 is uniform random, so is the first part of the output. And then you just apply the pseudo-randomness property of the second part. And what about the self-correction part? Well, S1 is much longer than S2. So if these two strings, the seed prime and seed, are close, then actually the first part of this seed, S1 prime, is close to S1. And therefore, we can recover a polynomial-sized list containing S2 by using this list-decodable error-correcting code from S1 plus CS2. And then we'll use this injectivity property to iterate over this list, find S2, strip off C of S2, recover S1. So it's straightforward. And just as a recap, we consider the symmetric case. And this is how you construct a scheme for just this setting. So let's go to the asymmetric setting. Well, let me first describe the asymmetric setting. You have these two channels and also introduce some notation. What is a BAC? It's just that the flip probability now depends on the input alphabet symbol. So your flip probability, you have one for 0 and you have one for 1. And similarly, you have an erasure probability for 0 and an erasure probability for 1. And you can represent them as these row stochastic matrices, where every row is labeled by an input alphabet symbol, and every column is labeled by an output alphabet symbol. And they give you these two stochastic matrices. And these row stochastic matrices you can think of as another representation, equivalent representation of a channel. Okay. Good. So now what's the construction for BAC? Well, it's going to be exactly the same as before. But just observe that previously we made this argument that from Eve's point of view, every string, the RS bot, every position in it was equally likely to be 0 or 1. Now, if you're in the asymmetric setting, this is not going to be true because you have E0, E1. So what you have to do is you have to change the initial distribution of R, this random string you sample and send through both channels, so that from Eve's point of view, it will be equally likely to have been 0 or 1. So for example, you'll sample 0, R sub I to be 0 with probability E0 over E0 plus E1. You'll sample 1 with probably E1 over E0 plus E1. And as a result, you also have to change the criteria for what constitutes being in the Hamming ball, because the initial distribution on R has also changed. And if you just do the arithmetic corresponding to the BAC, P0, P1, you get exactly this condition. And it turns out you might ask for when is it that we have non-degradation? When is it that Bob has enough advantage to recover M? And it completely coincides with this computation. So that's the solution, the exact same construction, and pretty much exactly the same hybrid arguments. So that's how you get BAC. Now the question is, why is this a central case? Any questions? Okay. So pairs of binary input channels reduce to the BAC case. And again, we're going to be viewing this matrix. So think of B as this 2 by n sub B matrix, and E as this 2 by n sub E matrix. And one could do some wishful thinking and say, like, OK, Bob is receiving some received string R sub B, but we really want to view this as some BAC. How would we do this? You could imagine Bob post-processing his output and with some other channel, with some other row stochastic matrix, to produce what is effectively a BAC. Now, if you did this, you would want a couple of properties to hold, or just 2 of them. You'd want to make sure that whatever you post-processed is not such that Eve can also post-process hers in the same manner so that it would eliminate any advantage you had. And on the other hand, it's a post-processing, so it's a degradation of the previous. So effectively, what you want to find is this channel post that turns your effective channel into a BAC, this 2 by 2 matrix, and such that you remain not a degradation of E. Okay. And just observe that if these 2 properties hold, any wiretap code for B prime E is also wiretap code BE for BE, just by these 2 properties. And how would you get to the BAC? Well, what we're going to do is we're going to imagine Eve's channel being split. and we're actually going to give Eve more advantage. So imagine Eve received her output from a BAC, from which she then simulates her channel. And in this way, we're effectively giving Eve even more power, but hopefully not enough to simulate B prime. Now the question is, can we find both of these, BACs and BACs? And we do this via this polytope formulation. And one way to think about why this polytope formulation is natural is because in these matrices, what we're effectively doing with this like channel post, for example, or the degradation condition, is that channel B, a matrix B, is a degradation of another channel if you can apply some post-processing, just multiplying by a stochastic matrix that gets you to the other matrix. And you can think of this polytope formulation, so let me introduce it, as exactly capturing this matrix multiplication. So we have the channel polytope where we start with any matrix of non-negative entries. And what we're going to do is just consider either the convex equivalently, the convex hull of all subset sums of columns of A, or you take any vector with entries between 0 and 1, and you hit A with all such possible V's. And this exactly captures, the second definition captures exactly this notion of degradation from the stochastic matrix point of view. So it's very natural. And the theorem we show in this paper, which I will not go through, is that if you have two arbitrary row stochastic matrices, then B is not equal to E times S for every row stochastic matrix S, if and only if you have this non-containment of the polytope. And this condition, B not equal to E times S for every row stochastic matrix S, is exactly the definition of degradation. So we actually have that channel B is not a degradation of channel E, if and only if the polytope, or really the polygon, is not contained in Eve's polygon. Okay. And this theorem really holds just for the case of 2. For the case of 3, we actually have an explicit counterexample, which is kind of interesting, that this polytope formulation does not extend to larger alphabets. Good. So here's a visual example of a BAC and a BAC. And all BACs always look like this blue and this red polygon. This blue one represents the BAC. This red one represents the BAC. And since the polytope is not contained in the red polytope, the BAC is not a degradation of the BAC channel. And from this picture, you can already see a visual proof of how to find a BAC in general. So if I start with an arbitrary blue polygon that's not contained in this red polygon, there's some extremal point sitting outside of the red polygon. I'll pick it, and I'll pick its twofold symmetry complement on the other side. And this will correspond to exactly those 2 points will correspond to exactly this rhombus, which will be a BAC that will that will still be contained in the original blue polytope, but will not be contained in the red polytope. So that's how you get the BAC. And now the question is how do you get the BAEC? That's kind of the more interesting question. For getting the BAEC, what we're going to do is simply observe, again, we have these 2 extremal points sitting outside the red polytope. And we just want to form, like you see this red polytope doesn't look like a BAC. It kind of has these many facets. And to form something like this olive polytope, we can simply apply the separating hyperplane theorem to get us this line and take its symmetric line. And this forms this olive polytope such that, again, channel B is not a degradation of it, while channel E is completely contained in it. So it is a degradation so channel E is a degradation. And you can find this polytope efficiently just by standard methods. And that's pretty much it. So some open questions. can we expand this construction beyond the binary input channel setting for dimension 3 and above? Because the polytope formulation completely fails. And can we realize these computational wiretaps coding schemes from hardness or from other cryptographic primitives? Something that we need here is actually like sharp thresholds. So if anyone's thinking about like average case complexity, that's also an interesting source of problems for this type of cryptographic primitive. And then the final question is, can we address this asterisk in the initial riddle, which is, can we de-randomize this encoding? And all of these are open. Yeah, and that's it. Great.
So you showed that I/O allows you to put basically to solve the problem in the regime of information-theoretic solution is not possible. So what about the converse? If you have any, I guess you cannot show that I/O is necessary. What's the best thing that in the converse direction? Can you show that implies boundary functions that any schemes for each?
That's a great open question. We do not know how to show that.
Even boundary functions.
Even one-way functions.
If reduction seems like the one. It seems like the naive thing might.
One-way function would probably follow from generic recipe, right? Just a pair of distributions.
Yeah, pair of distributions. Yeah, that's true.
Yeah, so other function.
The key agreement, for example, we wouldn't know.
It looks only function false. So do you have a conjecture? What is the right, this thing is opposite? I mean, I guess what's the right primitive to have something in the gap?
I personally do not.
Okay, that's
I
just,
do not have a.
where is
It's
it
a
from?
beast of its own, that's why.
Yes. Yeah. Great.
Okay, let's thank all the speakers today.
We have a reception in a few minutes.
Yeah, some snacks and more mingle.